Thank you for being here today. And yeah, I'm going to give you a briefly explanation of quantum optimization, just a general overview of what is quantum optimization uh, nowadays. So, okay. Okay, the presentation uh, follows um, these 4 points. I'm going to start giving you the motivation of quantum optimization. Then I am going to explain how can we translate the classical problems into a new form that a quantum computer can understand or can handle. And then I am going to explain a little bit about one of the most popular quantum approximation algorithms, such as uh, quantum um, variational quantum algorithm, uh, variational quantum algorithms, and then I'm going to talk about the limitation and opportunities of these algorithms. Okay, the question is why we are interested in addressing combinatorial optimization problems using quantum hardware. This is because that many of optimization problems, such as the knapsack, max code, portfolio optimization, are NP hard problems that if we try to solve those problems using uh, classical techniques, they quickly become computationally intractable. So we have some classical techniques that allow us to approximate solutions to these problems, such as heuristics. The problem with heuristics is that they can trap into local minimum. So this is one of the biggest problems with heuristics. But nowadays, we have quantum computers. Quantum computers allow us to see or to handle with optimization problems from a different perspective, and we can exploit uh, physical properties such as superposition and entanglement for addressing NP-hard problems. Okay, and the algorithms that I'm going to talk about today are designed to work on the current quantum hardware. So let's go to that. First, um, if you are familiar with this, with the workflow with combinatorial optimization problems and quantum algorithms, you probably know that the first step is to transform our optimization problem into the quadratic unconstrained binary optimization form. This this representation of, of the problems allow us to express a classical problem, let's say the knapsack problem, into a simple representation, a quadratic simple representation. Now the objective is to minimize this quadratic function that is in terms of binary variables. The binary variables are represented by x, and they are binary variables because they take values 0 and 1. These are very useful for problems, for combinatorial problems, because we can map the solutions using these values, 0 and 1. For example, in the knapsack problem, we can represent the solution the solution of an instance using a binary vector, and 0 represents that the item is not in the solution, and 1 represents that the item is in the solution. So in this QUA form, we can we can map our problem and using a quadratic matrix. The quadratic matrix is Q. This quadratic matrix contains all the information of our problem. Again, as an example, the knapsack problem has some values of the items. So the values of the items can be introduced in this quadratic matrix. So then many of the real world problems are subject to constraints, equality and inequality constraints. And the equality constraints can easily be introduced into the QUA formulation using just a quadratic term. But in the other hand, when we have inequality constraints, we can use two well-known methods. The two methods to deal with inequality constraints are slack variables. Slack variables allow us to express inequality constraints into equality constraints and then introduce that term as a quadratic expression into the QUA. Another method is unbalanced penalization. This method allows us to penalize unfeasible solutions of some problem. Again, let's think into the knapsack problem. Knapsack problem has an inequality constraint because it is subject to maximum total value that we can have in the knapsack. So we can easily use those methods to handle with these constraints. Okay. The second step is to represent the problem using spin variables. We want to represent the problem using spin variables because it allows us to write the classical quadratic function QUA into a new Ising Hamiltonian. This transformation can be done, and now the spin variables that we are going to have are -1 and 1. Now the objective is to minimize the energy of the Hamiltonian. So we are interested to find the ground state of that Ising Hamiltonian. So the ground state is the solution of our problem. Now, okay, let's start talking about quantum algorithms. The first quantum algorithm that I'm going to explain is the quantum annealing. Quantum annealing is a technique based on the thermal annealing. Thermal annealing is inspired into the process of heating and then slowly cooling metals in order to reach a uh, low energy state. Quantum annealing use or replace thermal fluctuation of thermal annealing with tunneling quantum effects. These tunneling quantum effects allow us to move through energy barriers and explore the solution space of the quantum optimization problem that we are trying to solve. Here in the right, we have one of the most recent quantum hardware from the company D-Wave. This is the Advantage 2 quantum computer that is specific for quantum annealing. Another approach that I am going to talk about is the variational quantum algorithms family, and this family of algorithms is based on the variational principle. The variational principle states that the ground state of some Hamiltonian is bounded by the expectation value of that Hamiltonian with respect any trial wave function. So this is the general workflow of variational quantum algorithms. And this is, we start here with a combinatorial optimization problem. And then we transform the combinatorial optimization problem into the quadratic unconstrained binary optimization model. Then we can map this QO into the Hamiltonian, and now we are going to be interested to minimize the energy of that Hamiltonian. But now we know that the energy or the solution energy is bounded, but this the expectation value of that Hamiltonian with any trial function. So now we need to do is to just try with different trial functions, and that's why the name of trial, in order to minimize the energy of that Hamiltonian. We can this process iterative, and this process has a classical part. The classical part is we have some variational parameters that must be optimized using quantum optimizers. For example, Covila. This optimizer is one of the most used in these algorithms. At the end of the process, at the end of a number of iterations, we can evaluate how good was the solution. And then we have here the first variational quantum algorithm. This is the BQE from variational quantum eigensolver. Variational quantum eigensolver is based on the variational principle that I mentioned before, and variational quantum eigensolver constructs a parameterized trial state, a trial function called, most commonly called ansat, using single qubit rotations gates and also an entangling gates. So this is an example of how a BQE looks like. And look that we have different parameters represented by theta. Those parameters must be optimized using quantum, sorry, classical optimizers. If this is your first time seeing these diagrams, you probably might think that is very abstract, this representation of quantum algorithms or quantum circuits. But let me break down into a most easy example. We have a variational quantum eigensolver for 3 qubits and just 2 layers. First, we have a single rotation qubit gates, and then we have a layer, an entangling gate. Entangling entangling gates. And look that we have the parameters that I have mentioned, and at the end of running this circuit, we will have measurements of each qubit. Then the measurement allow us to see a probabilistic distribution, and we then evaluate this final state using using the Hamiltonian in order to compute the expectation value, and then we have the final cost or the final energy of this circuit. After many iterations of optimizing these parameters, we will be able to minimize the energy of that system. BQE is one of the most famous variational quantum algorithms because it's also used, is very common when we have a molecule Hamiltonians, and this is very useful when we try to solve quantum chemistry problems. In quantum chemistry, we are also interested to find the ground state of a molecule. For example, we have here the water molecule. So we are interested to find the ground state of that Hamiltonian, that molecular Hamiltonian. Another very powerful approach to solve combinatorial optimization problems is the quantum approximate optimization algorithm. This algorithm is also based on the variational principle, but also is inspired into the adiabatic theorem. The adiabatic theorem says that if we start in the ground state of a time-dependent Hamiltonian, and then we evolve that system slowly, we finally have the ground state of the final Hamiltonian. So in terms of our problem, we are interested to be at the final of the evolution of the system to be in this Hamiltonian, in the cost Hamiltonian or the problem Hamiltonian. And then we are going to start in the in an initial Hamiltonian, and then we are going to evolve that Hamiltonian, time-dependent Hamiltonian, in order to get the ground state of the cost Hamiltonian. Most commonly, we choose this Hamiltonian, which is in terms of the um, Pauli X operators. So we commonly choose this Hamiltonian because its ground state is easily to prepare using just Hadamard gates. I'll show you an example of this, of how this algorithm looks like in a quantum circuit. So the first step um, to transform this time evolution into a quantum circuit is to construct this unitary operator. We are interested in unitary operators because unitary operators have the property to maintain the maintain states, the unitary property of the states. So we construct this unitary operator. Look that we have first the cost Hamiltonian, and then the other Hamiltonian that is commonly called the mixer Hamiltonian. At the end, we will have two unitary operators, and look that we have now another parameters that allow us to represent this time evolution. And these parameters, as well as the MBQE algorithm, must be optimized using classical optimizers. At the end, we will have this state. This will be our trial state of the UAOA algorithm. And look that we have another parameter P. P is the parameter that represents the layer of this algorithm. The more layers we have, the more powerful will be this trial state construction because of the adiabatic theorem. So then again, at the end of the layers, we will have measurements of each qubit, and then we have again another example of how this quantum circuit looks like. And then, okay, we start with Hadamard gates that allow us to prepare the initial state. This initial state is the ground state of the mixer Hamiltonian. Then we will have the unitary operator that corresponds to the cost Hamiltonian. And then we have another unitary operator that corresponds to the mixer Hamiltonian. These two unitary operators are in terms of rotations in the zeta axis of the Bloch sphere, and they also can be constructed using double rotations on the zeta axis. Okay, To visualize how quantum variational quantum algorithms work, I prepared an example with uh, um, this famous device that is called the Galton board. And classically, the Galton board works with just um, fall balls through through the these pegs, and at the end we would have a normal distribution uh, of the balls, right? But it is very similar of how variational quantum algorithms work. Let's think that we have first circuit initialization and initial state, and this is how can we throw the balls, right? We can change the initialization state, just changing the size of this ball, and we have then the ansatz of the algorithm. The ansatz can be represented using this peg distribution, and we can change the size of the pegs, we can change the distribution of the pegs, and this is how classical optimizers change the parameters, the variational parameters. At the end, as I mentioned before, we will have a measurement, and what we are going to measure is this a distribution, a probability distribution, and we are interested in the solution that with higher probability. Okay. Variational quantum algorithms and quantum annealing are not perfect because we have some limitations, some current hardware limitation that limit how can we run bigger experiments and in quantum hardware. That is because we have noise and decoherence that lack the how good are the results running these quantum algorithms. And yeah, these three methods struggle when we scale in the number of qubits or with as the problem instances grows. So, but we are now in the exploration state of these algorithms. So we have now a lot of researchers doing his work in order to improve how these algorithms perform, right? So variational quantum algorithms like PQE and QAOA also have problems with non-convex optimization landscapes. So these algorithms can lead to local minimum for this kind of non-convex landscapes. And another key aspect of these quantum algorithms is that quantum annealing is constrained by a specific quantum architecture. That is the quantum annealing architecture that we saw before in the D-Wave computer. And in the other hand, we have that BQE and QAOA can be run in the quantum gate based hardware. So yeah, we are, as I mentioned, we are still in an exploration stage of these algorithms. So we have a long way, a long path to move through. So one of the approaches that we can do in order to improve the performance of these algorithms is to work in noise mitigation, for example, in order to get a better solutions at the end of running these algorithms. And then one question that I think commonly arises is that if quantum algorithms replace classical approaches, and the answer is no, but we can combine two approaches in order to exploit the best part of each one, right? For one side, we can use quantum circuits in order to explore the solution space, and then we can use classical optimizers to optimize parameters and improve the performance or feasibility. And yeah, as we saw before, quantum variational quantum eigensolver is most commonly used in molecular energy estimation, and quantum annealing and QAOA are more focused on combinatorial optimization problems. And how can we improve these algorithms? We can improve the design these algorithms, modifying the ansatz. For example, in the QAOA, we saw that we start from a mixer Hamiltonian, and we can design different circuits just changing this mixer Hamiltonian, and the solution will be depend will depend on how we design these ansatz. So yeah, and we have work to do on noise mitigation in order to improve the performance, and yeah, we can use, for example, adaptive optimization that can enhance the outcomes of these algorithms. So yeah, thank you for your time, and I hope that you learned something new, or uh, or yeah, or um, I'm very happy to share my ideas in these kind of events with, and where we can discuss about some of the current state of quantum algorithms. So yeah, thank you for your time, and that's it.
Thank you, Jorge. We do have some questions for you in the Q&A chat.
Okay.
Okay. First one. Why is Cobella better for VQCs? Oh, wait, hold on. I think we have someone who wants to ask you a question.
Okay.
Yeah, thank you so much, Natalie.
Hi,
Thank you so
Alberto.
much for your presentation, Jorge. I had two questions, if it's okay.
Yep.
So, yeah, what do you think is the best idea to use QA compared with BQE? Because, like you explained before, the QA is a particular case for BQE. But in what approach or what characteristics do you think is better QA?
Okay. Um, yeah, QA, as you mentioned, is uh, a particular BQE, a particular case, and this is QAOA is more powerful when we have combinatorial optimization problems because the cost Hamiltonian can easily be used to construct the QAOA circuit or the ansatz. And in for example, BQE, we don't have any information of the problem. We just have a random state, and we just will try to optimize the parameters in order to minimize the energy. But it is like more um, try, try and measure, try and measure. So yeah, for combinatorial optimization problems, I would say that QAOA is more powerful. But BQE can be more powerful if we deal with problems like quantum chemistry problems, because there are now new ansatz based on BQE that allow us to enhance the performance of the BQE in order to tackle this kind of problems.
Hey, and thank you so much for the answer. And just another one is like you put a limitation for the hardware is in a certain characteristic at the moment you're working with this kind of applications. So, in your experience, what kind of a characteristic or limitation you're working right now in your project? Do you think is the problem is the number of the qubits, the depth, the noise, or yeah, what is the your experience? Yeah, related with the dealing with the hardware.
Okay, from my experience, I would say that the problem is when we deal with uh, large instances with many qubits, with problems that require many qubits, we will have also very large ansatz. I mean that we will have ansatz that have many gates, and the depth of the circuit uh, grow uh, grows very fast. So yeah, if we have more and more gates, we at the end we will have very noisy measurement. And for the coherence, we we don't have we would like to avoid very large circuits. So yeah, this is from my experience.
Okay, thank you so much, Jorge. Thank you so much, Natalie. Yeah, thank you.
Yeah, thank you, Alberto.
Thank you, Alberto. And thanks again for this morning. Okay, so back to this first question I had for you.
Yeah.
Why is Cobella better for VQCs?
Okay. Um, Covila is most used because it is a pre-gradient optimizer. The landscapes of these kind of problems are very strange, so it's hard to compute the gradient when we are doing this classical optimization. So yeah, Covila is a pre-gradient and allows us to estimate or doing well classical optimize task without the gradient. That way is very powerful for this kind of problems. Yeah, I hope to ask your question.
Okay, great. Thank you. And someone is asking, are you okay with sharing these slides with us, Jorge, after the presentation?
Yeah, sure.
Okay, great. And next one, what are some common strategies for optimizing the QAOA parameters? And is QAOA purely a quantum algorithm, or can it be treated as hybrid in nature with any classical optimizer?
Okay. Let me share again the presentation. Okay. The first, the QAOA is a hybrid algorithm. That means that it is not purely a quantum algorithm. It has a classical part, which is the optimization part. And how can we optimize these parameters? Okay, we have this trial state that can be represented using a quantum circuit, right? As the quantum circuit in the presentation. Okay, let's say that you have 10 iterations for solving some problem. In the first iteration, you will run your circuit. At the end of running this circuit, you measure and you evaluate how good was the expectation value of the Hamiltonian. Then the classical optimizer update the parameters, and then in the next iteration we will have a new optimization parameters, and yeah, just that's it. And the optimizer will update the parameters in each iteration based on the expectation value of the cost Hamiltonian. And yeah.
Okay, cool. I have another question. We have 3 more for you.
Okay.
Let's see. Why is the bin 011 the most populated in the 3-qubit Galton board quantum simulation?
It was just an example. It was just to visualize how this a visual example can work to explain how operational quantum algorithms can be viewed. Yep.
Great. Thank you. Thank you for providing all of these circuit images. I know it's they take a lot of time to make, so it's a lot, and getting them on a presentation is definitely requires some effort. So thank you for providing those.
Yeah.
Another one we have is how can a false qubit initialization affect the ansat's performance?
Sorry again?
How can a false qubit initialization affect the ansat performance? Yeah, if the person who asked that wants to provide any follow-up info.
Okay.
But until then, the next question is
Okay, it's just I don't understand the first part of the question. The what? Qubits?
the false qubit initialization.
Oh, okay, okay.
Okay, yeah.
Yeah. Okay. How these affect the performance? Okay, we have, for example, in this in the QAOA, we can start from a different ansatz that I wrote here, and the initialization of the states allow us to approximate to the final state more easily. Well, if we have if we would have some clue about the final state, we probably choose a mixture Hamiltonian that could be more aligned with the final result. And with this information, we can easily construct or initialize the state in order to approximate faster the solution. So yeah, it's just to improve how can we approximate to the final solution. Yep.
Okay, great. Last one for you before we let you go. In control engineering, systems get represented in state space matrices. What are the most used quantum algorithms to solve complex control system problems?
I'd like to answer this question, but I am not very familiar with control systems. So I would say, I don't know. I am so sorry
That's
for
okay.
that. But yeah, I won't lie to you.
Yeah, no problem. But thanks everyone for providing your questions. If there's
Yeah.
any more questions for Jorge, you can send them in the chat. But otherwise, can we just please give him a great big thank you for presenting and being the concluding presenter of our day 2.
Yeah, thank you.
Yeah, thank you.